Okay, good morning, good morning. Welcome back. Happy Wednesday. So there are some announcement things I'd like to discuss, but we'll wait until more people trickle in today. We'll just dive in on page 34. If we take our quick look at the calendar, today we're going to talk about density and center of mass, two ideas from physics. And again, we're kind of in the middle of this. You can just sit any place. Yeah. So we're doing all these applications of the integral, and so apparently that's going to come up today with density and center of mass. Just a quick reminder that quiz number 4, which became a take-home quiz, is due right now, so throw it in the folder. Also, project 5, the one with the 4 chocolates, is due on Friday. So I've seen some people have made some good progress with those chocolates. Some people have made good strides using regression on the calculator to try to come up with formulas for curves that approximate these crazy shapes of the chocolates. So that's good. On Friday also, I'm going to hand you project number 6. It is already on the table. If you wanted to grab one early, you can. And that's the coming week. Any questions about the calendar? Okay, so let's just go ahead and do those announcements now. So first one is just a reminder that currently the student government elections are happening here at GCC. So log into Moodle, read the platforms of the various candidates, and pick the people that you think should represent you here. And also there's this referendum regarding MassPerg, and it is going to be a yes or no. You can read some information on Moodle about that as well. Any questions on this? It was supposed to end today, March 27th, but because there was a little technical glitch on Monday when it opened a little late. So this goes until tomorrow noon is the last time you can vote. All right, so log into Moodle when you can and go ahead and vote. Next thing is about Advising Day. So Advising Day is coming up this coming Tuesday of the next week, and there are no day classes that meet on Advising Day. There instead is a whole long program of stuff that you can take advantage of. There's lunch. I think I saw like something about massages here at the end of this document too. I'm back. Yeah, 10 to 2 free chair massages. So if nothing else gets you here, that should. And in addition to coming in and taking advantage of this full program of activities, it would also be a great time to meet with your academic advisor and plot out a schedule for you for taking classes in the fall and possibly also in the summer if you're interested. So I'm going to share with you a very brief snippet of an email that the person who is number 2 here at GCC sent out. First is Bob, our president, and then Cher is right underneath. And she says, encourage your students to meet with their academic advisor and enroll in courses that will best move them toward their goals and degree or certificate completion. Students may not be aware of new Pell lifetime funding requirements. We talked about this a little bit last semester that make accurate course selection more important than ever for students on financial aid. So I don't have all the details, but some of you shared with each other last semester in a couple of our classes about that. So really important to make progress towards your degree and goals. If you don't know who your advisor is, you can go see this person, Julie, or you can just ask me right after class and I can tell you who your advisor is. Again, Advising Day is this coming Tuesday, all day. You can register for the fall and also the summer. Print schedules, print listings of all the classes should be available soon. I don't have a date for you, but if you go onto the main GCC webpage, you can search. All the classes are up there for the summer and the fall. Any questions about schedules or Advising Day? Okay, so let's go back to here. Right, so we're on page 34, and 34 begins with this idea of density functions here in number 1. Can we go to Steve? Okay. Thank you. So basically the definition of density is this one right here. It's just the mass of the thing divided by the volume of the thing. If something is more dense, then it's got more mass in the same volume, say. We talked a little bit about density on the very first day of Calc 1. when we looked at how a lake froze, and it turned out that the more dense water, of course, sinks to the bottom of the lake, and the less dense is up at the top. And that was really important in terms of the lakes freezing from the top and not the bottom. And so if the density is mass divided by volume, then the mass must be the volume times the density. Okay, so that's basically a definition of density. We're going to go ahead and jump down here to number 3. I'll say that we'll do a whole slew of problems today related to this idea. I think that number 3 is the toughest one, and it's also the most interesting one. We're going to just kind of be using formulas for much of the rest of today, but let's see if we can try number 3. Go to Sam. Okay, so lots of stuff going on in this question. Let's start by just drawing a picture and trying to understand what it's asking. So we begin with a cylindrical barrel, so we'll just draw a cylinder. And then we'll start filling in some of the attributes of this cylinder. It's good enough. So it says the diameter is 7 feet. As soon as you give me a diameter right away, I write down the radius. The diameter is not in any formula that I know about things that are round. So the radius of this cylinder is 3.5 feet. And the height of the cylinder is 21 feet. Oops. So 21 feet top to bottom. And it's filled to a depth of 10 feet by muddy water. So a little less than half of this thing is filled. So there to there is just 10. And we're going to answer a very, very simplified version of this question first, and then we'll answer the tough question that's in front of us. Suppose that the density of this water didn't vary, but instead, let's just say the density of the entire bucket is going to be 80 pounds per cubic foot, just to make this problem much easier than it is here. If the entire bucket is 80 pounds per cubic foot, how would we figure out the weight of all of the water? What would we need to calculate? We need the volume, right? If we can find how many cubic feet of water are in this bucket, we'll have some big number in front of us. And what do we do with that 80 pounds per cubic foot? What are we going to do with it? We're going to multiply, right? Find out how many cubic feet we have, multiply by 80 pounds per cubic foot. Every cubic foot is 80 pounds of weight, and that'll be it. That'll be the weight of the whole bucket. So we can do that pretty easily. So here's the way easier version. So the weight of the whole bucket is going to be the volume of the whole bucket times 80 pounds per cubic foot. All right, how are we going to find the volume of all the water in this bucket? Pi r squared, I'm going to write times h first, but everybody knows the volume of a cylinder, right? Pi r squared h. And then that's going to get multiplied by 80. And I've stopped writing the units here, but I'll just highlight what are the units for the volume of this bucket? Cubic feet. When I multiply them by pounds per cubic feet will cancel, and we'll get a certain number of pounds, which is the weight. That's what we're after. So we can fill this in, and we'll just get a number. So this is equal to pi times the radius, 3.5, that gets squared. The height, 10 or 21? 10, just the water, right? So times 10 times 80. And if somebody could give us an estimate here, that would be helpful. Any questions on doing the far easier version of this problem? Okay, so what makes this problem tough is that the density, this 80 pounds per cubic foot, is not constant. That's just the density of the particles or molecules. Which one should I use? What is water? Is it a molecule? A particle? Molecule? Both. All right. So the molecules of water down here at the bottom are very dense. There's all this sludge down there at the bottom. It's fallen to the bottom. So at the bottom, it's 80 pounds per cubic foot. But then the molecules of water that are just on top of those ones are a little bit less, maybe 79.9 pounds per cubic foot. And the ones at the top, where the water is as clean as it's going to be, what's the density up there? Is 30 pounds per cubic foot. So there really is quite a bit of difference in the density of the water at the bottom and the water at the top. I can guarantee you that the real answer, the real weight of this thing is going to be less than the 30,000, right? Because we picked the most dense stuff at the bottom. If we wanted to get an underestimate, we could replace the 80 with 30 and we'll figure out, all right, it's definitely more than this other number. But how are we going to do it here? Well, the idea is we're going to slice this water in such a way that the molecules of water in our slice all have pretty much the same density. So generally, there's only like two ways to slice something, either go vertically or horizontally. Right? So if I were, for example, to slice this way, so imagine cutting the barrel like that, do all of the molecules in the water in that slice have roughly the same density? No, they vary wildly, right? The density at the bottom is the 80 and the density at the top is the 30. That's not a good slice. You want to slice it in a way that the density doesn't really change too much in the slice. So if instead we were to slice it this way, I'll go ahead and draw the circle so we can see it. What do we believe about every particle or molecule of water in that circle? It's all the same density. I don't know what it is, but they're all the same, right? Because we're given that it's 80 at the bottom and 30 at the top, and it just varies linearly in between. Garrett? Yeah. It is. And so that's actually the easy way to answer this question without calculus. So we're going to do that last to check our answer. That's a good insight. Exactly. So if it was a parabola, then it would be much harder to find the average density of the molecules of water. Great. Thank you, Cole. Okay, so that's our slice, but our slices always have a little bit of thickness. So I'm going to draw a much exaggerated slice. I'm going to draw the top part of it way up here. So for all the water between those two circles, the density is roughly the same, although it's way exaggerated. It would really be like a piece of paper, like very thin. And then we could say pretty confidently that the water in this slab, that slice, is all pretty much the same in terms of density. So it feels like the density of that water depends on what? How far up it is, right? So it seems to me like it's time to introduce a variable here. So how about we'll call x how far up it is. So from there to there, give a name to this height, how far we are. What would be a good symbol for the thickness of this slice or the slab? Maybe delta x, right? It's a small change in x. So delta x I'll put up here. It's just the thickness of the slab. If you want to call this one, I mean, yes, it's a vertical thing, so you can call it a change of y, but I guess what I would do is say, use whatever letter you already used. Okay, so I guess what I'm interested in is a couple of things. So first, how about we find, but we're still using this basic equation here, that the weight, but now it's of a slice, is the volume of that slice times the density. So we'll write that. So the weight of I'm going to call it a slab instead of a slice. It's the same idea, but that slab of water is definitely equal to the volume of that slab times the density of the slab. So we're going to find these two things. So how about we'll start with the volume of the slab. What kind of math shape is the volume? Is that red slab? What is it? It's a cylinder, right? I mean, it's a tiny cylinder. It's like a penny, but it's a cylinder. So the formula for the volume of the cylinder is the same as it was before. It's just not the whole cylinder anymore. It's a tiny cylinder. So pi r squared h, But now these things, well, one of them is going to be different. What is the radius for every slab? That's 3.5. It might change in some problems, but in this case, it's just a constant, 3.5. We gave a name to the height of a slab. We called it delta x. Good. So that's it. Nowhere else to go from there. We've got the volume of our slab. We still need to calculate what? The density of the slab. So I'm going to start using the symbol that your book uses for density. Density of the slab, and that's the Greek letter lowercase delta. In our simplified version of this problem, we assumed that all the water had the same density and it was an 80. But here it's going to change. What is it going to be based on? Yeah, we're going to have a linear thing like a y equals mx plus b, and I appreciate the use of the letter x because x is exactly what determines what the density is. So what we need to do is figure out a formula, a y equals mx plus b, for the density. So how about we just make a quick chart, and this is not the only way to do this, but I like to make a quick chart, density, which is delta. So we have information about the density of two particular x's. What are they? 0 is the water at the bottom of this tank, and 10 is the water at the top. So we're going to use those two numbers. What is the density at 0? 80. And the density when x is 10 is 30. And so we'll find the equation of the line that hits those 2 points. So Cole had said y equals mx plus b. I'm going to change one of those letters. What do we have instead of y? We have our delta. So delta equals mx plus b. Delta equals, okay, so calculate the slope. What is the slope? So negative 5x, sorry, negative 5 is the slope. Yes. Changing y over changing x. Negative 5x plus. And then the b is the y-intercept. It happens to be given here. What is it? It's 80, right? Because x is 0, so the y-intercept is 80. So that right there is the density function. Negative 5 is doing the slope calculation. So we're doing change in y over change in x. 50 over negative 10. Okay, so I'm going to put that density function right up here, negative 5x plus 80. And now I think we're good to go. So let's go ahead and write down, so I guess I'm doing this guy right here, the weight calculation. So the weight of a single slab, we said was the volume of that slab times the density of that slab. We've already figured out the volume of a slab. What is it? Times delta x. I'll underline that in red. It came from that thing up there in red. Times, we need to multiply by the density of a slab. So it changes. It has x in it, but what's our formula for the density? Negative 5x plus 80. And I'll underline that in blue because it came from this thing right here in blue. Any questions on any of those pieces? All right, I'm actually going to change my equal sign because technically it's not going to be perfect because the density in a slab changes just a tiny bit. You know, it does have a little bit of a thickness. So the weight of one slab is going to be approximated by this thing. If I want to find the weight of the bucket, I can approximate it by adding a bunch of slabs together. So I'll put this step in. I don't really need to see it written out like on a test or quiz or anything, but the weight of all the water is going to be approximated by a sum of things that look just like that. So I'm just going to copy that whole thing right down here. And another little technicality that, again, I'm not worried about in terms of any kind of grade, but traditionally you give an index to anything that has an X on it. So just so we can count the slabs, slab 1, slab 2, slab 3, X1, X2, X3. Let I go from 1 to some number of slabs. We'll call it N, some generic thing. And in order to make our approximation really good, what are we going to do with the number of slabs? Send it to infinity. And when we send that kind of thing to infinity, when you have this sum, what does it turn into? It turns into an integral. So let's write down our final formula here. So I'm going to write here the weight of the bucket. And now I'm going to put equals, the true weight. It's not approximately anymore. It is going to be exactly equal to a certain integral. The integral is just all that stuff we wrote in purple, but remove that silly subscript that we put in there. Pi 3.5 squared. What does the delta x become? It becomes a dx. I'll stick that at the end. Negative 5x plus 80. Okay, and the last thing we need to put here are the limits on that integral. So just imagine taking your generic red slab and sliding it up and down to take care of all the water. What's the x value for the bottom slab? 0, top slab, 10. Those are our limits, 0 and 10. Okay, so you can find this integral without any technology. We'll let a couple of people just find us an answer. And while we're waiting on an answer, so first, are there any questions? This is a very lengthy process, but I think I don't have just like a formula I can give you that says, okay, here's how you answer when you have a muddy bucket of water, and here's how you answer when you have some different kind of varying density thing. For me, it's really about the first principles. Slice the thing up in an appropriate way, find the weights individually, slap an integral in front of it, and you're done. But it really is a thought process. And I'll give you an opportunity to really do one of these kind of involved things on Project 6, which we'll give out on Friday. Maggie. No, I won't take points off if you don't put the approximation sign. Thank you. Anybody have a number for us? Okay, and this is a weight, so it's in pounds. And that seems reasonable to me because when the bucket was made up of the most dense stuff, just to make it easier to find, we came up with a weight of about 31,000 pounds. So this is maybe 2/3 of that. That seems okay. And then Garrett had given us an idea for maybe being able to do this without going through all the calculus and the slicing at all. Garrett, can you say again what you said before?
Take the average of those numbers.
Average of which two numbers? Yeah. So yeah. So there is in this case a non-calculus way to do this thing. it's pretty clever to just recognize, okay, if the heaviest stuff is 80 pounds per cubic foot and the lightest stuff is 30 pounds per cubic foot, and it varies linearly in between, then we can calculate what the average density is of all the molecules of water here. And if you average 80 and 30, you get 55 pounds per cubic foot. So what you can do is essentially cross off this 80 and just make a 55. In this line, we calculated the volume of the whole bucket, all the water, pi times 3.5 squared times 10, the whole 10 of height. Multiply it by 55, and you're going to get exactly the number that we had down there at the bottom. But I do like Cole's observation there that only works because in this case the water varies linearly from 30 to 80. But if it varied in any kind of other way, it would be much tougher to find the average density of a molecule of water. Any questions on that? Okay, so when you're ready, we'll go to the next page. And before we look at the next page, we'll just share a couple more artistic masterpieces that some folks came up with for the three-dimensional solids of revolution. So this was Andrew's contribution. Thank you, Andrew. Some folks in the other class actually gave me names of their artworks and they kind of described the motivation. Do you have anything? I don't mean to put you on the spot. Looks like the top of a chess piece, maybe, if we rotate it a little bit. What is it? Strange mushroom. All right. And then Garrett, do you have any thoughts? This is yours right here. Yep. You guys see that? Cool. Thank you. Okay. So let's come back here and we're on the next page now. So there's a challenge question there about car density. So you might check that one out later. I think it's a nice question. We are going to kind of skip around a little bit here. Yeah, let's just look a tiny bit at number 4, but we're not really going to do number 4. So can we get Dawn? Can you read the first 2 sentences of number 4? Okay, so let's come down here now and we're going to jump into number 7. So I've got this diagram of a seesaw, but what's unusual about this particular seesaw? The little pivot there is not in the middle, right? For the seesaw, the pivot is in the middle, but that's no good unless you have people sitting on either ends that weigh the same, right? That's the only, otherwise it doesn't work. So if you have the girl who's only 25 kilograms and the father who's 75, the father will always sit on the ground and the girl will be flailing around up in the air on the other end of the seesaw. So that's no good. So how about we try to think about where we can put the pivot, it's not going to be in the middle, to make it so that it balances. Do we buy that, at least in this picture, that the center of mass should be somewhere closer to the father because he's a lot heavier than the daughter? Okay, so then the question is, where should we put it? Now suppose that I tell you that the whole seesaw is 8 meters long or 8 feet long, whatever it is. So do we have a sense based on the 25 and the 75? So Garrett says 2. A couple of other people are saying, yeah, it should be like a 2 this way and then a 6 over there. More than 2? Yeah, there's a ratio thing happening. The father is 3 times as massive as the daughter. We need the father to be 3 times closer to that center of mass, and that's true. And so in physics, there's a name for this kind of thing. It's number 5, and we'll go to Dave. Okay, is that something you guys have done in physics? Yeah, this semester or last semester? Okay, is that the definition that folks remember? You had equations for it? Anybody remember the equations that we had for it? What was it?
Perpendicular force times distance.
Okay, so force times distance, force times distance. So force is ma, right? So, and the a is a constant here on Earth. So multiplying force times distance is basically the same as multiplying mass times distance. And then Josiah, you said something about 0? Yeah, so if the thing is going to be perfectly balanced, then the sum of all those products there is equal to 0. I Okay, cool. Right, so Josiah, you can read us number 6, please. Okay, so let's see if that's true. Some of us kind of intuited that this should be a 2 and a 6 for this particular seesaw. So if we decide we are going to call the left-hand side here 0 and the right-hand side here 8, just imagine the x-axis there, and then we'll start calculating this kind of this moment business. So it's supposed to be mass times displacement. So let's do the moment of the daughter and the moment of the father. So mass times displacement, but I think it's equivalent to force times displacement that you guys did last semester. So the mass of so we're doing mass times displacement, daughter's mass, 25, times displacement from the pivot. We're saying it's 6 in this case, right? How far? 25 times 6. Sorry, I have mislabeled my stuff. Okay, we're good. Yes, 6, but the daughter is on the left of the pivot and the father is on the right, and so we need to pick one direction to be positive and the other to be negative because this is a displacement, not a distance. So let's say that the daughter is on the negative side to the left of the pivot. So we'll say 25 times negative 6. So that is, yeah, so imagine the y-axis here. So probably calling 0 and 8 was not such a good idea. 0 is at the center there. So the daughter is sitting at negative 6 and the father is sitting at positive 2 according to what we kind of intuited. All right, so that's a negative 150. It's a number that represents the tendency of this seesaw to pivot towards the daughter, negative 150. Great. Now we'll compare that to the moment of the father. Again, it's mass times displacement. Father's mass, 75. Father's displacement, 2. Father's moment, 150. And this is the 0 thing that Josiah was talking about. If you have balanced things, then all of these moments added together will be 0. Everything will cancel. So, so that's good. If we come down here, we will get another, we'll get a formula that we'll be able to use. Number 8, come up here to Tacity. Okay, so we're going to use that formula. It shouldn't be clear where the formula came from. If you wanted to actually come up here and maybe solve this problem, like we just wrote 6 and 2, and then we verified that the sum of the moments was 0. But if we wanted to actually do some work here, maybe you do something like it's listed. X would just say that we're going to put the daughter X units to the left. You can cross that off. I had an L in there to be general, but 8 minus X would be the other stuff. And then you can do a calculation to figure out how much is X so that the sum of the moments will be 0. And when you do that kind of calculation, you'll end up with stuff that looks like the formula that Tacity just said. Bubba. We do need the 2 sigmas. Yeah, it's a good question. So Bubba is asking, is this thing down here, is this sigma the same as a single sigma with a 1 fraction. Bubba, is this what you're asking? Yeah, so unfortunately, summations don't work nicely over division or multiplication. So you can't combine those two. So yeah, the m's would cancel, but it's not allowed, even though it seems reasonable that we should be able to mush them together. So let's use that formula on the next page. And we'll go to number 9. Joe? Okay, so the center of mass again, so we're going to draw our seesaw. And we're going to say that the center of mass is here, and we're going to pretend that we don't know what the center of mass is. We're just going to call it x bar. And the whole thing here is 8. So this is the part where I'm going to go ahead and just redefine 0 at the far left and 8 at the far right. And then we're going to make sure that the center of mass is at exactly the right spot so that the sum of all those moments is 0. And we're going to come up with the answer we got before. How much is x bar in this picture? Where is the center of mass? It's at 6. So we're expecting the answer is going to be 6, but we're pretending we don't know it. And we're just going to use that formula that kind of came out of the blue. So the 25 kilogram girl is there. 75 kilogram father is there. So x bar equals, so it was the sum of the x's times the m's divided by the sum of the m's. Okay, so let's start writing some stuff down. We're multiplying the position of a person times their mass. What is the position of the daughter? What number? We put her at 0 this time. She was at -6 when we kind of knew the answer before, but here she is at 0. So it's a 0 times her mass, 25, plus summation. Now we're doing the father's position. What's the father's position? Is it 8 times father's mass, 75. And that gets divided by the sum of the masses. Sum of the masses is a 25 plus 75. So go ahead and do that calculation out. Upstairs, what do we get? So upstairs is a positive 600, downstairs is 100. Lo and behold, the center of mass is 6 units in, 6 units from the daughter. So again, it's kind of mysterious how that worked because I just threw this formula in front of you. The sum of the x times the m is divided by the sum of the m's. But again, you can kind of verify that it's working if you redo that problem from the previous page. But x times m, that's the moment. So somehow it's related to the sum of the moments and also related to the sum of all the masses. Okay, so now we started today with a calculus question where we found the weight of the muddy water. None of these problems here with the seesaw have any calculus in them, but instead of imagining point masses like we have 2 people sitting on here, what if you imagine some kind of continuous thing like a rod which has different densities throughout, right? Maybe it's very massive at the start, and then it gets less massive towards the middle, and then it gets more massive towards the end. So that's where the calculus is going to come in. So we'll go to number 10 for coal.
What if there aren't discrete masses, but instead there's one object varying? How would we compute the center of mass? Suppose an object is lying on the x-axis between x equals a and let delta x density of an object at point.
Okay, so let's take a look at this picture. So you've got this rod here going left to right, and its mass is not distributed uniformly. If it were just distributed uniformly, then the center of mass would be in the middle, and that's how it is for many objects that we encounter all the time. But we're going to pretend this one has varying density. And so the idea here is, okay, well, we talked about density with the bucket of water at the start of class. So suppose that you, you picked like a really thin kind of slice in here. Would you agree that if it were thin enough, then the density of all the little molecules in there wouldn't change very much inside of that little slice? And so if the density doesn't change very much, then we're kind of like these slabs of water. And we started off by finding the weight of the bucket of water, and it was the volume of the slab times the density of that slab, right? So it's the same thing that we're doing here. It's not weight though, we're just gonna get a straight mass thing, but it's proportional to weight. And so it is the, not volume, but thickness of the slab times its density. So it's the same calculation we did before. We did volume times density, now it's just thickness times density, because we're not in a three-dimensional thing anymore. So the mass of that little thing right there is approximately equal to the density at whatever point you're sitting at times the thickness of the slice. So the summations from our last formula, so I've got my last formula written up here at the top of the page. So we're just going to replace. So this guy becomes x bar equals, so that blue summation form, that blue formula up there. Instead of the sum of the x's times the m's, it is now the sum of the x's times, but instead of the m's, I now have an approximation. The mass is approximately equal to the density at the point times the thickness of that slice. So we're just going to replace. Instead of m sub I, density at the point times the thickness. That's divided by what? The sum of the, so from the original formula, it was the sum of the m's. But again, we're going to replace the masses with this approximation over here. Delta xi, delta x. So all we did is copy this formula from up here, but instead of that, we used this. It was here, and it was also down at the bottom. Everybody see that formula getting replaced? Joe? All right. Yeah, it's unfortunate. We use the capital delta for a small change. I quite like that for the thickness. We're using a lowercase delta because the word density starts with a D. You can use rho. Actually, your book might, I think your book uses rho for something. Rho was density in physics? Yeah. Yeah. Something. Okay, so, but absolutely, you can change the lowercase delta to some other symbol if you'd like. And then what we'll do is make these slices really, really thin so that we could use infinitely many of these slices here and get a better and better approximation for where the center of mass is located. When we do that, what happens to the summation on the top? It becomes an integral, and the summation on the bottom becomes a separate integral. And so we're just going to get two integrals. It's going to look a lot like this formula that's mostly highlighted here. If delta x is the density of an object lying on the blah, 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 then x bar, the center of mass, is given by integral of x times delta of x. Do you see that from this green highlighted formula? There's the x times delta of x. What happened to this capital delta of x? It became the dx. And downstairs, the density times the delta of x, there's the density, and it became a dx. So actually answering problems using this formula is kind of a letdown because it's going to be like cake easy to just plug and chug into the formula. The important thing to me is that we understand that the integral is an appropriate tool here because we're slicing in such a way that we pick things that have just about the same density in the slice. And then when we add up all of those, we do these different summations, they become integrals. The calculus is going to be a letdown at this point. Like actually doing a calculus problem is just really easy. So let's try 11 and then we'll do the group thing. So 11 will go to Angus. Okay, so let's try this one here. So I will draw my x-axis, and then we'll go ahead and draw a rod up there on the top, 0 and 2. And it says the density is 5 plus x squared kilograms per meter, where x is how far you are from the left-hand side. So if x is 0, meaning you're sitting at the left-hand side, how much is that formula? It's 5. So the stuff on the far left of this rod is 5 kilograms per meter. If you're at the far right of the rod, then the x is 2. Again, x is just the distance from the left. When you plug 2 into that formula, what is that? 9 kilograms per square meter. So it's going from 5 to 9. Is it going linearly? It's not. It's a 5 plus x squared. So let's just do one more number. Let's look at the middle number. If this was a linear thing, then what number would be in the middle in the green? Would be 7. Let's see what we actually get. When you plug 1 in to that formula, what do we get? 6 kilograms per meter. So it's not a linear thing. So unfortunately, we couldn't do like a find the average density of all the molecules in this rod. Do we have a sense then? Is the center of mass going to be to the left of the middle or to the right of the middle? Heard a couple of votes for right. Other votes? One more for the right. It's not always easy. It's not easy to necessarily just think about. You really have to kind of puzzle over it. If it were perfectly average and there were a 7 in the middle, then the center of mass would be right there in the middle. Half of this rod is between 5 and 6. Great. But half of the rod is kind of much heavier, much more dense than that thing. So it feels like the center of mass is going to get tugged just a little bit to the right. So let's use the formula, but like I said, it's it's quite boring to use the formula, but we'll get a number here. So we're just doing an integral of x times delta of x. What's the delta of x formula in this problem? It's the 5 plus x squared. And then from where to where? 0 to 2, that was given. Divided by exactly the same integral, but missing what? Missing that x in the front. So we get 2 easy integrals. You can do them by hand. You can do them with the calculator. I'm just going to write the answers because there's really nothing to do, but 14 divided by 12 and 2/3. And that is approximately 1.105. That's where the center of mass of this rod is. Unfortunately, it's the same answer to Bubba's question for the same reason. Integrals don't work well over division. Yeah. Yeah, you'd get the integral of x. Yeah, it just doesn't work, unfortunately. Okay, and I think our intuition was confirmed here. The center of mass was a little bit to the right of the center of this rod. Any questions on this? It's really boring to use that formula, right? Like there's nothing to it. Like it's like insultingly easy to use the formula. So that like the goal of today is not to say, can you use the formula, because that would be like a 30-second class. It's all the stuff that kind of led to that formula.
On the bottom, that's just give you the total mass.
It does.
So it really is just the same formula.
The same formula, this one up at the top.
Well, it's like moment arm times mass over average.
Yeah, it's exactly the same formula. Yeah, so it's a very natural thing to go from the summations when you have finitely many things to, oh, it's infinitely many. It's a continuous thing. It's just integrals.
So yes, in a way, it's like each of the moment arms times the average mass.
Each of the moment arms times the average mass. Yeah, instead of dividing by the total mass. Yeah. Okay, so there are analogous formulas for 2- and 3-dimensional regions. You can take a look in the book, you'll find them. Let's see if we can work our way through this activity. First, we're going to, we'll read it, and then you guys will go to town trying to find the center of mass of a very strange object. So we're going to go to Chris. Okay, so let's see if we can imagine this kind of crazy ruler. So in between the 0 and 1 inch mark, there is a solitary penny sitting right there. Between the 1 and the 2, you will find 2 pennies stacked on top of each other. Between the 2 and the 3, there are 3 pennies stacked on top of each other, and so on until you go between the 11 and 12. How many stacks of pennies are there? 11, 12, 13. It's one of them.
You put 12 stacks of pennies.
That's true. I did, and I don't generally lie. So there are 12 stacks of pennies. And just kind of count and convince yourself that just to the left of 1 is the first stack. So just to the left of 12 will be the 12th stack. So we got 12 stacks of pennies, and I want to find where the center of mass is. Well, if the ruler were not part of this equation, if the ruler didn't have any mass at all, then it would be pretty straightforward to find the center of mass. Which penny would you be looking for? What's that? So we could figure out how many pennies there are. 12 times 13 divided by 2, 6, 78. There's 78 pennies here. Which penny is going to be the one that represents the center of mass? There are 78 pennies. The median penny, the 39th penny. If you can just find where the 39th penny is, then you'll have a same number of pennies to the left as to the right. Yes? But the problem here is that there's a ruler sitting underneath it. And the 39th penny, is the 39th penny going to be closer to the left-hand side of the ruler or the right-hand side, or will it be perfectly in the middle? It's going to be further to the right. Most of the pennies are further to the right. Yes, there's a stack of 12 pennies here at the end. So the middle penny is going to be further to the right on this ruler. But the further you get to the right, the less ruler there is out there kind of contributing its own mass. So the idea here is that it's not so easy to figure out exactly where this thing will balance, because it's not just the pennies. The ruler also contributes, and it contributes, you know, kind of like in an equal, nice way, but not distributed the same way as the pennies are distributed. So in terms of masses, there's one part of this that I want to highlight. Yeah, the ruler itself has a density of 1 penny per square inch. Probably square is not the right word. 1 penny per inch. Yeah, equivalent. That's essentially what we're doing here. We're adding a penny to each of the stacks. So on the first stack, there's just a single penny, but there's also the mass of the ruler sitting underneath, and we're going to say that the mass of the ruler is 1 penny's worth. So the mass in that first inch is 2 pennies. The mass of the first inch is 2 pennies, right? The actual penny plus a penny's worth of ruler. And in the second inch, there's 2 pennies plus the ruler, which will always contribute 1 penny per inch. So that next inch is basically how many pennies? Is basically 3 pennies. What's that? Yeah, yeah. Okay, so on the next page, you are going to find the center of mass of this ruler 2 ways. You're going to find it using the discrete kind of formula way, this summation way, and then you're also going to find it using a calculus thing, and then we'll compare those 2 answers. So I'll walk around and help if we get stuck, but see how far we can get on this page. Okay, so check in with each other as you try to answer number 1. So we'll just interrupt real quick. I know folks are making good progress on this first part, but Chris, thank you very much, said that my median penny idea oversimplifies the problem. I had suggested that the center of mass, if we could ignore the ruler, would happen at the 39th penny, like the middle penny. But Chris points out that you know, we had said that the middle penny is going to be, you know, someplace skewed to the right, which means that the pennies way to the left are much further from the center of mass than the ones on the right. And so in my mind, I just had a perfectly balanced seesaw with 39 pennies on the one side and 39 on the other with the pivot right in the middle, but that's not accurate. The center of mass will be further to the right. So scratch the stuff that I had said about the median penny. Thank you, Chris. Okay, so just a couple of groups had a question about, is there an easy way to type this thing into the calculator? So just to be clear, does everybody have something that looks like this on their page? At the half-inch mark, you have 2 pennies worth, the penny itself plus the 1 penny of ruler. At the 1.5-inch mark, there's 3 pennies worth. And then be really careful at the end. You got to make sure you stop at the right spot. So at the 11.5-inch mark, there's a stack of 12 pennies plus 1 more penny's worth for the ruler. So there is an easy way to type this into the calculator, and it involves the sequence command and the sum command. And so we'll talk about those too, but in order to use them, we need to be able to write these blue things as a formula. So we need separate formulas for these numbers as for these numbers. So we're just going to say, so we just need a formula for 0.5 and 1.5 and 2.5. So can somebody give me a formula that will give me those? It'll have x in it. 0.5 plus x, is that fine? And where do we start this guy? Starting at x equals what number to give us the first one? 0. And then ending at x equals what number to give us the last one? Is 11. So we're going 0 to 11, which is equivalent to 1 to 12. It's fine. But 0.5 plus x takes care of that. We want to come up with now another formula for the numbers in the parentheses, but we're going to use the same x, which is still running from 0 to 11. So the guys in the parentheses are just going up by 1. So I feel like, again, it's going to be a 1x plus something. Starting at x equals 0, what do I need to add to get the 2 in the parentheses? Add 2. When x is 1, how much is this x plus 2? Is 3. So that takes care of it. It's actually kind of funny that we ended up with this 0.5 plus x, because I saw several people in the next question come up with the density function. That's essentially what this thing is the density function. But several people came up with an equivalent, but not this density function. Had a 1.5 plus x, which is totally fine. But we'll use this. So then the idea is that each of the blue numbers here looks like 0.5 plus x times an x plus 2. X going from 0 to 11. Folks see that? Multiplying the first number by the number in the parentheses. 0.5 plus x times x plus 2. And now it's in like calculator speak. So we can input this into the calculator. So with the calculator, we're going to go first to the sequence command, which is inside of list, which is right above stat, second list. And we have these 3 options up here, names, ops, and math. We go to the right. And down there in number 5, we see the sequence command. So the syntax for the sequence command is you tell it the expression you want to evaluate, which is that stuff in the blue parentheses over there. So we're doing parentheses 0.5 plus x, close parentheses times x plus 2, close parentheses, comma. Then just like the integral command, what do we put next? X, the variable, comma. Just like the integral command, starting number and ending number. In this case, x is going from 0 to 11. And the default is by 1. If you put a comma and then some other number, it will go up by those things. So I don't know if these numbers look familiar to you, but if you did any of this blue calculation out, how much is 0.5 times 2? 1. 1.5 times 3 is 4.5. And you can, it doesn't look like it, but you hit the right arrow, you can scroll to the right. And the last one for us was 1.5 times 13. Nope, sorry, 11.5 times 13, which you can check is the 149.5. And then to actually get the number here, we want to go back into list, and this time go to the left, and then sum, number 5. And then second, whoopsies, that's not what I meant. Number 5, not doing good things here. Over there, number 5, sum of answer is what I want. So second answer. And 683 is the. Did I get it wrong?
I got 2. It's 689. I keep getting 683.
Yeah, I got 683 too.
Yeah.
That's why I wanted to do this.
Yeah.
Is 7.65 right, or is that wrong?
No, it's
7.588.
It's 683.
Yeah, seems like I made a mistake. So I know we're out of time, but if you have, say, 60 seconds, I do have a ruler that I'd love to just bring around to the table real quick to